Hi, I am Shanaz. In this lecture, we are going to prove Nakayama's lemma. But before we prove this lemma, let us recall what we did in last lecture. In last lecture, we proved a result which was like this. So, if M is over finitely generated A module and I is an ideal in A and phi is an endomorphism on M with the condition that phi of M is contained in IM. Then we proved that this phi satisfies an expression of the form phi to the power n plus a1 phi to the power n minus 1 plus so on plus a n minus 1 phi plus a n is actually 0. So this is what we proved in last lecture, where these ai's are in I. In particular, these ai's are in ith power of I. So this is what we proved in last lecture. Now we have an important corollary to this lemma, which is like this. So let M be our finitely generated A module. So let M be a finitely generated A module and I be an ideal in A such that this IM is actually equal to M. Then there exists some element, say A in A, such that, let us call this element X. There is an element X in A such that X is congruent to 1 mod I. Now X is congruent to 1 mod I means that the difference of these two elements, X and 1, is actually an element of I. So this is if and only if condition, and this X annihilates M. So let us prove this. So we are going to use the previous result to prove this corollary. So prove. So let us take phi from M to M, the identity map, which is obviously an A module homomorphism. Then phi of M is actually M, which is equal to IM. So this phi satisfies the hypothesis of this result. So then phi satisfies the expression i.e. phi to the power n plus a1 phi to the power n minus 1 plus so on plus a n minus 1 phi plus a n. So this times some element M is 0 for all M in M, or this is same as phi to the power n times M plus so on plus a n minus 1 phi M plus a n. This is equal to 0. But phi being an identity map we have but phi being an identity endomorphism on M, we get 1 plus a1 plus so on plus an times M is 0 for all M in M. So let us take this element, let us write this here, where ai is in I for all I. So take x to be equal to 1 plus a1 plus 1 plus an, then x times M is 0 for all M in M, that is x annihilates the module M. Also from this expression over here we have, so also if we look at this element here x minus 1, this is actually equal to a1 plus so on plus an. Now all these ai's being element of I, so this is an element of I, or x is congruent to 1 mod I. So this proves our claim. Now let us prove the Nakayama lemma, and the statement for this lemma is as follows. So we have Nakayama's lemma. Actually this lemma was proved by the Corollary, and somehow this lemma is named after the Nakayama. I don't know why, but this lemma was actually proved by Corollary. So for this very reason it is sometimes called the Corollary Nakayama's lemma. Now this lemma states that, so the statement is like this. So let M be a finitely generated A module and I be an ideal in A, I be an ideal in A which is contained in the Jacobson radical, of A. Now note that this Jacobson radical is by definition the intersection of all maximal ideals, where M is maximal ideal in A. So if this is the case, then I am equal to M implies this M is the zero module. So let us first see what we are given, what is our hypothesis. So this M is our given a finitely generated module, and I is any ideal which is contained in the Jacobson radical of A. Then I am equal to M implies this M is actually a zero module. So let us prove this. So suppose im is equal to m, and let phi from m to m be the identity module homomorphism, be the identity of endomorphisms of A, endomorphisms of A. This means that this phi is actually the identity module homomorphism. Then by previous result, I mean by this result over here, we can find an element x in M which annihilates M and is congruent to 1 mod I. So by above result, there exists some x in A such that x annihilates M and this x is congruent to 1 mod I, that is x minus 1 is in I. Now there is the characterization of the Jacobson radical, which states that an element is in Jacobson radical if and only if 1 minus x times y is a unit for all y in A. So this is true for all y in A. In particular, this is true for when y is equal to 1. So x is in Jacobson radical will imply 1 minus x is a unit. So since now x minus 1 being an element of I implies 1 minus x is also in I. So since 1 minus x is an element of I which is contained in the Jacobson radical, would imply 1 minus, now this is x over here, so this would imply 1 minus x times y is a unit in A for all y in A. In particular, 1 minus x, which is equal to x, is a unit. Here we are taking y to be equal to 1 because this is true for all y in A. Now if this is a unit, then m, which is equal to x inverse x times m, which is same as x inverse times, now xm is 0, which is 0, that is this m is the 0 module. Now x being a unit, we have it is inverse in A, so this implies this module m is 0. Now we have the following corollary to this result. So let m be a finitely generated A module and a submodule of M and I an ideal of A contained in the Jacobson radical of A, which is JA. Then m is equal to I m plus n would imply that m is actually equal to the submodule. So let us prove this. So note that this I m and this n both are submodules of m. So since I m and n are submodules of m, by second isomorphism theorem we have, by second isomorphism theorem we have, so if we look at this, so im is a submodule, n is a submodule, so their sum is a submodule, and this submodule contains the submodule n. So this will be actually isomorphic to the quotient module im mod im intersection n. So this follows by second isomorphism theorem. Note that the intersection of two submodules is a submodule, so this is a submodule of im. Now let us define a map. So define a map phi from im to I times m mod n by, so phi takes an element here which is of the form am, so it maps this element to, now this a is an element of I, so this maps this element to a times m plus n. Now this m plus n is an element in this quotient module. So it is straightforward to prove this phi is actually an a module homomorphism, not only homomorphism but a surjective one. So clearly phi is a surjective homomorphism. Now let us exhibit the kernel of phi. Also, kernel of phi is the set of all those elements in im for which phi of am is actually the identity here, the zero element, which is n. So this is in im. So let us rewrite this. So it is the set of all those elements in im for which this is true. So this is the set of all those elements in im such that a times m plus n is n. So this is actually equal to the set of all those elements in im for which this am is an element of n. So those am and im for which this am is in n. So this is actually the intersection of these two submodules. Now let us invoke this first isomorphism theorem. Then first isomorphism theorem implies that im mod its kernel, which is im intersection n, is actually isomorphic to I times m mod n. So this is hash. So if we compare star and hash, so comparing star and this hash, we get I times m mod n is actually isomorphic to this thing, which is isomorphic to im plus n mod n. So im plus n mod n. So since im plus n is equal m, we get, so we have I times m mod n is equal to, so we have to replace this by m, so this is m mod n. So now we can invoke the Nakayama lemma. So in place of m in Nakayama lemma, we have m mod n here. So for im is equal to m, we have I of m mod n is equal to m mod n. So this implies hence by Nakayama lemma, hence by Nakayama's lemma, m mod n is actually the zero module, or this means when we mod out m with n, we get zero module. This means that this m is actually equal to n. So this proves the result.